Thank you very much. I guess thank you, Raul, for introducing me and telling everybody I'm getting old. It's okay. So this is, I still have a few here left, Raul. Thank you again. So good morning, everybody. Nice to be here in Japan. We all figuring out where the room was and how do we come here. So this is some of the work I've been doing recently at Maryland. I've been dwelling into multi-robot problem for a long time. And so this talk is a little bit of my experiences, and I would say recently, last 3-4 years, we're going to be using a reinforcement learning. So I'll just share my experiences with that. But this is still it's a very old, hot topic right now, what we call multi-agent reinforcement learning. How do we do it? Some of the work I'm presenting today is actually done by my PhD student, Senthil, who has actually been graduating soon. So I'll present that. But this is 2024. I was having a discussion with some of my collaborators this morning at breakfast at the hotel, Joan and Maggie, Multi-robots are finally getting deployed, right? This idea is not new. And a couple of examples I've seen the example of Amazon warehouses, right? They're deploying, from last I heard, I was actually visiting one of them, they're deploying, Amazon is using close to 750,000 robots in their warehouses. And while a lot of the stuff is confidential, but I heard some of them they're using up to many hundreds of robots at the same time. Of course, we always worry about Amazon environment is more constrained because they can make warehouse to be robot friendly and they have a cloud system. So we see that. There's also an example that the company in India, I've been talking to them quite a bit, they do the drone shows and they take hundreds of drones, like inauguration for, let's say, some national event like Republic Day or something like that. But most of these large scale things, and I think I was learning this morning, there was a big DARPA program offset, they also had a huge deployment. So people are at least doing physical robots of the tens of even hundreds of robots in space or in thing, and they're doing it. But except they are very controlled, they're like very, very controlled, especially in Amazon, they have a cloud and a very constrained environment, So the challenge here is, when can we go for very distributing? And I'll come back to it. So just go to basic 101, something been around for 25, 30 years, There are two classes of methods. You teach an undergraduate or graduate class introductory, centralized method, right? So you've got multiple robots. You'll see me use the symbol MRS. And the first class example is centralized. There's one server. An example of this I always look at is your airport runway, right? There's a tower, somebody sitting there. You got 3 or 4 runways, maybe at the Tokyo airport. I just came from DC last night, 3 or 4 runways, single human telling which plane land, which plane go. So it's like a very centralized control. And once you give a clearance, now you can land. So that example, of course, that person do it. So the challenge with centralized system is, you can't scale them. Now, what we're seeing in Amazon is a little bit, they have a cloud constraint. And even the company who does the drone show, it's kind of like they have a predefined path for every drone. I don't call these drones as fully autonomous. They're just following a path like that. And of course, something that I've been very excited about for the last 20 years is decentralized, where every agent independently moves around. They have a partial knowledge of the thing. They walk each other and learn. And two of the problems which actually got me into this area about 18 years ago, I was looking into how humans move, traffic, right? Most of us are coming the day one at the conference, right? Employee like me, you went to the other building, got your badge, and figuring out where my NX F201 is, right? And with the rain, you're walking around, you follow each other, and we come, oh, you're the same location, right? Or you drive traffic, right? Traffic and human crowds are example of that. And for a lot of birds in nature, I'll show that too, do things. So this is where it comes out to be. So the focus is, actually, I want to do more decentralized because, as I said, I've been motivated by how pedestrians and human drivers navigate and a lot of animals in nature navigate. And somehow they figured it out, right? Day one, we're confused, we're jet lagged. If we're here for the conference 2-3 days on the road, we'll be just so familiar with it, right? We'll be going back and forth to this location, next workshop, and where lunch here with the exhibition very easily. So the challenge here is, and humans go, not just humans go. Many years ago, I was working with a group in Saudi Arabia. They have this annual ritual of Hajj. And before COVID, more than 2 million people were going for the Hajj. And at that scale, you can't even count, more than 2 million people. They come, do the ritual, just see how many people gathering in like a city and walking and doing the ritual around. So for some nature, humans are able to do it, and birds and do it, they deal with it. So it comes up there. So what are the challenges, if you want to build multi-robot system like decentralized, like we see all this biological and traffic, the first problem we talk about is, I come from motion planning background. What's our rule number one? Motion planning, the path should be collision free, right? You should not bump into each other, do no harm. The path should be smooth. The path should follow kinodynamic constraints. All those issues come up there, Now, especially if you're carrying big payloads, let's say if I go to Amazon warehouse, they're carrying these big carts, they can't afford a collision, like collision at no cost. That's it. No things there. The thing other which comes up is, when a lot of people come and crowd for the space, you have deadlocks. In fact, we did some work with Amazon, even a single robot, and they're putting an Astro in your home. Even there, you come across deadlocks, and how we're dealing with that. But they should work independently. And again, as I said, the challenge here is scalability. How big do you want to be? So the two kinds of method, this is a pretty long topic. And if I start surveying, I'll need a full half an hour, which I don't have time. But I tell you two kinds of methods that in robotics that we have dealt with. There's also the work in, this problem also studied something called pedestrian dynamics. There's something called social forces. People have studied that. And they're also working in crowd simulation, the other crowd model like cellular automata. So there are lots of methods, but in robotics, the two kinds of methods I'll do. One is for all of us coming from control background, MPC. It's a very powerful method, and people use it all the time. You plan the trajectory over a time, agent neighboring position, and you basically do some kind of optimize based on collision, smoothness, and progress. The second kind of idea, which actually goes back to a paper by Fioroni and Schiller in 1998, they did this notion of velocity obstacles to basically how you move around and avoid collision by velocity. We started a lot of work based on their plastic work, but actually when we started working in 2007, but then one of my students went and discovered the literature, what we call velocity obstacles. People were navigating ships like that 100 years ago, except they did not use the term velocity obstacle. So the idea was not new. Although the name was, Fioroni and Schiller did 1998 paper velocity obstacle, we did RVO, the ORCA. But what's the thing in ORCA, we were trying to do? Basically, in this case, we know the state of every other robot nearby. You look everybody, you know where they are, and you know how they are moving. And based on how they're moving, you compute some kind of a geometric optimization. You see constraints like this and do it. And this is something we played with it, and we created a conservative version by, actual problem is nonlinear optimization, but with a conservative approximation by linear programming, become very cheap. So every agent decentralized is taking less than a microsecond and moving in hundreds of agents. And we did a lot of simulation, it worked well. Actually, we were trying to do robotics problem. I don't know how much success in robotics, but the gamers took it. The gamers love it. If you look at any game engine, Unreal, Unity, play a game, they license the code and it's become very popular in gaming. It was a surprise, like a lot of robotics ideas become useful outside robotics. Now, more recently, as I was saying, with MPC, so one of the robots which I've been playing a lot, we work with Amazon Lab 126. They have a consumer robot called Astro. How many of you have seen or heard about Astro here? Amazon has some pretty nice web pages on YouTube, right? And they've been selling it slowly. So this is a robot. It's actually a very, very challenging project. They're trying to sell a robot for $1,500, which should work in your home. My God, everybody's home. My home is messy. My wife complains all out, right? Robot has to deal with it. You make a mess, everybody different layout, you change the furniture, you drop the cables, all the iPhone charging cables on the floor, robot has to deal with it. Plus, they have to work on a very cheap hardware. Like a lot of the machine learning we do on GPUs, they don't have a luxury of a GPU, they have a low-end CPU. So they use something called MPPC. This was the work of Jonjin Park. He's actually at Amazon, he did a lot of it. They're doing it. And they do these robots like this, except, even this is a whole class of MPC extension planner, single robot, but they run into what is called T-corridor in home. You have situation like you go to the door, suddenly, no, I'm not telling you, I'm just showing an example, it's okay. The robot goes and suddenly somebody comes in. It's like a T-junction. You don't see somebody, right? Or like a deadlock. So they want this robot to work around with it. So even there, we deal with like some of the work, which actually presenting later in ICRA this week. How do you come up with the MPC methods we can avoid, collision-free or deadlock-free? So this is classical optimization using how you do generalized probability. And with a lot of work on MPC, this is not the focus of my talk, but I just want to show it to you that you can even deal with narrow passages. And actually they come at situations because now they're making thousands of robots and sending to everybody's home. You don't know what your home is going to be, how your furniture layout. So here's a basic planner like MPPC, suddenly goes behind the sofa, and you can see this is a single robot game, and it gets stuck, or it becomes overly conservative. But we say if you do better collision probability on the right, this is a paper my students will present later this week. No, we can do much better job and do thing. So at least for a single robot, even in challenging environments like this, these MPC methods, MPC class of methods have become quite well do it. And other thing they don't have to do is freezing. But again, same way, we have a working solution now which can even deal with very challenging situations because otherwise they'll freeze. No, they don't. So you're seeing this solution being used in consumer robots, which are coming up, working in everybody's home, and one of the things I like about them is that I'll talk about learning method. Learning methods have a lot of benefits and challenges. One challenge of learning method is you need a big GPU and compute power and explainability. This is much more explainable and has low compute requirements. That's there. Now, as I said, we also did a lot of work on ORCA-like methods, something we have studied for 15 years. And one of the benchmarks we introduced, and we do it, the most common benchmark we use is put n agents around a circle and tell every agent to go to diagonally opposite location. And we did up to 10,000, scale it up, just as it. So this is the example you'll see, that how they're going when they come. This is when the congestion occurs. So this is like the classic example of really testing a decentralized method, something like this happens here. And of course, if you do different situation, even the ORCAs are being conservative, you're in a deadlock situation. So this is the classic 101 with decentralized method. Every agent is making his or her independent decision. They come to narrow space and a deadlock or a chaos occurs. This is congestion, right? In fact, one thing I learned about congestion is, if you want to what's the best way to solve congestion is, do all the hard work doesn't happen. It's like traffic jam. Once traffic jams occur, you have bad luck. Do everything to avoid traffic jams. Like people are doing Waze apps doing that. So that same thing comes up here. So that brought us to, we started doing RL-based navigation. Why do you want to do it? Well, RL is cool, right? I joke with my students nowadays, very hard to get a paper in ICRA accepted if you don't do machine learning, right? And if you do machine learning, they still pick on you. Why do you not do 100 comparisons? But if you don't do machine learning, you could have done it, right? So there's a lot of work on RL for navigation. I'm sure you find lots of wonderful papers at ICRA, So a couple of things, clearly single robot, they do it. One thing RL has shown is, if you can choose the right reward function, do the right policy optimization, we have seen some very impressive results. Something we could not do 10 years ago. There were a lot of success stories. And also, they deal with a lot of sensor data. You got perception sensors like cameras, LiDARs, or some of the sensors, it do it. So that definitely, added a lot of benefit to it. But one of the things we're looking into is that how do we do multi-agent RL? That's been a hot topic now, MARL. You'll see multi-agent, what can we do it? And the two big challenges that we deal with in this case is besides all the RL-based challenges of, policy reward function, policy optimization, how do you have a parameter thing? But basically, how do you communicate and cooperate? So ideally speaking, someday I will have a decentralized system which will be totally decentralized, but I don't think such a system is possible, or at least not in the near future. And even humans, I'll tell you, communicate to a certain extent. So one of the challenges of this talk I'm going to talk about is dealing with communication and these kinds of problems here. So there's some initial work we did initially a couple of years ago. We were dealing with the warehouse problem that suppose you got a lot of robots and they go to all the jobs, you got hundreds of jobs. So we looked into multitask allocation. How do you assign the task? Like in the Amazon warehouse, a robot goes and brings this car to A to B, B to C, something like that. They are whole day they're running 24/7. So we did a lot of work on building reinforcement learning this problem. And the basic idea was that at a high level, we modeled the Markov decision process. And we found out if we choose rewards based on minimum total travel time, it works well. And then, of course, we designed both centralized and decentralized system because I'm not going to say today one is better than the other. They both have their pros and cons. And in fact, but people are doing some hybridization. But, this is a kind of example of, you got a whole bunch of tasks in a warehouse. You got thousands of tasks, delivery tasks. So think of Amazon warehouse, something like this. Here's an architecture, a single RL agent for task allocation, allocate the task. And at the low level, we use the ORCA for decentralized, or we use some basic simple centralized, and we do a reward function. But the key here was that if you do task allocation based on RL, single RL-based agent Markov, we had some good success. And I won't go details into that, the papers are there, but we look into some very challenging layouts of, complex layouts of obstacles in white you see there, and it worked quite well. So that gave us quite a bit of confidence that at least RL-based some situation there, but we are not doing fully multi-agent thing. The work we're doing more recently is looking into multi-agent RL, and this is still work very much ongoing area, but I want to take 3 questions to keep in mind. How do they cooperate? All agents could be working towards the same goal. How they compete, sometimes to accomplish a goal, and sometimes people bring teams. You got a red team and a blue team there. So here's the example I have. Also remember, you're dealing with real-world robots, and you have partial sensing. You have a robot swarm operating to rescue individual here as a partial observer of the environment. And this, how can the robots coordinate? Especially if you're given not a good map of the environment. A lot of time, at least in the simulation, or the Orca example I showed you, in the gaming world, I have a perfect layout of the world. That makes my life so simple. Unlike I come here, I'm still figuring out where annex room 201 is, where registration is. Life gets much harder. So one of the questions I've been looking quite a bit is, we need to have some communication, because I just think if it's totally decentralized, every agent is like blindfolded to everybody else, you're going to have deadlocks, and you're not going to get anywhere close to optimality. So the question that we're looking quite a bit to is, and this is where a lot of work has been. The example I showed you about a few slides, all the Amazon example are mostly centralized, because decentralization is a combination of that. So we're looking at partial knowledge decentralized methods, and in fact, I would say our 2 motivation has been how humans do, or human traffic do. Believe it or not, one way or the other, humans implicitly communicate with each other. You're just following where everybody's going, right? I was just coming, where is my convention center? I was just following Joan this morning, right? Joan, you rescued me, right? I said, Joan, must be going to the conference. I did a lot of hard work here this morning, Maggie and Joan. Traffic, right? You look at the person next to you, you follow that. The person next to you going fast, you'll go fast. So there is always a lot of communication, explicit, implicit happening. And our goal is to do, how do we bring this communication in the MARL thing? So one of my most challenging problem, which I've been dealing for 10 years, and I still don't think we have looked at it. One of the most thing I've looked at is this problem of murmurations. I'll just show you a video from YouTube and see if you've not seen it. So this has enamored me a lot for many years and someday. So this is the video. So sometime in the fall, people will record this video somewhere on the top part of North America or Northern Europe, other parts of the world. And you see these wonderful emergent behaviors, right? There probably, I can't count, maybe thousands of birds. This is purely my guesswork. Do you think the birds are communicating with each other? If so, in what form? I've seen some prediction that maybe every bird looks at local information, where everybody is. Just there's some local, we don't know exactly, but the conjecture is that everybody's following some basic, simple rules, looking next to each other and doing it. And then the amazing thing is this global pattern emerges. And nobody understands, in few cases, in ant swarm, we understood simple ants, but even the control theory, people are like, what give rise to this kind of pattern? So, but the question is, there is this murmuration. So this is the example of, one of the most challenging decentralized problems we can see. So this is the much different words like this comes here. So probably they look at each other, local sensing. We don't have a biology to look at it, but we're putting that to work on it. So let me go back to my talk here. And the challenge here is, that how do we build this communication MARL framework? That's where the question comes up here. So basically, one communication, communication challenge is there. First of all, expensive. Looking at a scalable system, right? We're going to have hundreds of agents. You can't have every agent communicating n-1. Then you need n-squared communication bandwidth, and that just won't be very practical, right? And then there are latencies here. So also, one of the goals we're looking into is what is called selective communication or limited communication. How many communication do we need? And of course, there's observation, the overlap. We want to minimize that. And communication 1 to B, A to B, B to C, C to D can cause cyclic dependency. So there are challenges coming up in this framework right here. So the question that we're looking into, and this is still very much work in progress, when to communicate, because we want to be communicating, we want to be very selective in the time space. What to communicate, right? Should it be my current position velocity? At least when I talk to Amazon people in cloud, they have localized every robot. So you know every robot at any stage in the warehouse, where is what robot and what's it moving toward. You know the location quite well. So that's a very specialized case. When you're driving, you have a rough location of people next to you before you make a lane change. When you're walking, the same thing there. And whom to communicate. So this is the three big challenges: when, what, and whom, right? As I said, this decentralized method communication here, but especially if you don't communicate, you're going to see deadlocks like we saw in Orca. That is going to happen, especially in tight situations. So we want to overcome them. So one of the things we're looking into is, how do we communicate effectively for coming up with RL-based simulation? So one is to do coordinate decision making and to improve the partial knowledge, because we want to do some intelligent communication in the network in a restricted sense. We want to be as efficient as possible, this thing. So we are kind of, I would say, looking at solutions which are trying to optimize these four characteristics. That's what we are trying to do and see how well we can do it. And I said, I'll suggest our work, but there's no way, I'm sure many of you can propose better methods, and that's where the field will evolve. So the idea is, what we're looking into is like intelligent communication performed in a multi-lane framework and do selective. We want to be very selective in a non-grid world setting, because a lot of these settings, like we saw, at least Amazon warehouse, they're a very selective grid world, but we are saying, no, we can't make just, humans don't move in a grid pattern, humans move things. Traffic, even in some part of the world, is very irregular too. And basically, some of the off-the-shelf methods may not be very suitable for these kinds of situations. So they're different. We're not the first people. As I said, there have been a lot of papers on RL-based and multi-RL-based method. The one example is from one by, this Xiong Ma's group, and also the well-known method of Jonathan House coming out of what we call CAD-RL, which is well one we compared with there. So, we are looking into assumptions of decentralized multi-communication. The robot GALE is what we call selected neighbors. So every robot has a few neighbors, which will they do it? And we can handle the number of variable numbers of neighbors you want to do. Do you want to do 2, 4, 8? Of course, the more you share, the more information you communicate, you make the navigation strategy better, but the more you share, also expensive. There's a pain of there and there. So what we really do in this case is, we keep track of a traditional like state, P for position, V for velocity. You're given roughly the states, in this case, the radius is thing. The observed state is position velocity, but there's some hidden state. You don't exactly know. You might know the local goal, but you know the global goal of this person, and you don't know what preferred velocity they want to go with. That's what happens there. So this is our current architecture. I won't go to details of that. The papers are on the web right now. So you have 4 parts to it. There's the ego agent state, occupancy map, neighboring state, and communicated message. So this is kind of architecture comes up. There are a lot of things. Senthil spent a lot of my time on this, designing this here. The 2 parts I want to talk about is there's a whole selective communication. We want to really multi-head self-attention. And then we have a message aggregator. So this is where the essence of, where the selective communication is occurring, which we're not going to the details of that, but this is where the design of the method comes up there. So trying to do a lot of communication scheme, we are doing centralized training and decentralized training. The main goal was scalability. And the whole idea is that every agent has some observation, but by communicating, we're augmenting that by selective communicating. But we notice that even small amount of communication can considerably improve the performance of the decentralized navigation in terms of deadlock reduction and time to goals, quite a bit well up there. So literally, how do we do it? Especially one challenge in all the MARL method is, how do you design your reward component? And sometimes, one of the challenges writing to avoid convergence. Sometimes the training goes on for 2 days and things go like this. That's where things are there. So these are different reward function. Now, there are a couple of parameters we look at. I'll focus on 2 things here. One is the number of communication link, how we come up. But the second is we want to give a communication penalty because we want to minimize the weight, communication. So if the weight goes up, that's not a good news. And you see, this is how I'm looking at the communication overhead. This WC minus NL in the reward function, we take into account as a negative term and account for it. So just to give you some examples, how we spend a lot of time training with it and looking into, multiple agents. We'll agree that to 4, 8 agents. And sometimes, even for up to 8 agents training, it can take a lot of episodes. So this training cost is not cheap, and you better have some good GPUs to do it. So let me show you some evaluation results and see how it goes. So here are some examples. You'll see the left two are our multi-agent reinforcement learning. You can see in the very left case, I'll play this again. I want you to focus on this reward communication overhead. See if you have some communication, if you are a little bit, how the behavior changes on the thing on the leftmost there. And just for comparison, this CAD RL and the R leftmost is the RVO, like the basic multi-agent, where you have much more deadlock, but we get much better distribution of paths with the MARL. So MARL really give good examples. Here's some more kind of benchmark where previously RVO had deadlocks on the right there, but on the other hand, our new methods, with very little communication are doing promising results. So this is really what promises us to really pursue this line. We are seeing some good trends with multi-agent reinforcement learning. The kind of deadlocks we're facing with RVOs, our previous method, we're not seeing it. So clearly there are situations, there are benefits to this, where they are basically this DSMA of a new multi-agent responding planner navigates to final configuration successfully and does a pretty good job. Whereas the previous method, including the CAD-RL from other reinforcement learning and RVO, they are deadlocks. So clearly we're seeing promising of better decentralized navigation behavior from this multi-agent reinforcement learning. So that means we should continue working on that. Not only that, one of the factors I told you, we want to see emergent behaviors, right? Now, of course, murmuration, the limit of emergent behavior, we're nowhere close to solving that. But you see here, this is our example with this thing. And you can, if you really see, the trajectories are pretty well distributed. This is the kind of trajectory I want to see. If all the agents go into the center and cause kind of, congestion, that is not a good news, because as is the best way to solve congestion is avoid it. But if you come back here, you see this here, they literally do a much better job and go around the same way. No collisions, not close proximity. So this is giving us a lot of hope that this kind of architecture with selective communication can indeed help us provide good solution to emergent behavior problem. Here are some more examples, static lane formation, the random obstacle lane forming, and cooperation. You see, this is the example of what, multi-agent classically, there you got a whole bunch of narrow corridor. If you don't prioritize them, in the previous case, you're deadlocked, but here, how do we give a right of way and able to do it? So this all kind of situation we can do quite well. And these are just some numbers just to show you, one of the comparison here is like to give you, this is a best case scenario, time to go is lowest, but we're getting a very high success rate, close to 100% even with 30 edges, 0.99 to be precise. Whereas previous method, whether RVO or difference reinforcement, single reinforcement learning method like 2, have much lower rate. So what this is giving us, this high number is telling us that if you're able to do some amount of selective communication MARL, you can indeed get good results. That's our conclusion so far. And that's how we're outperforming all these previous methods. So this is just to some more numbers, communication penalty, number of agents come up here and how distribution of agents, a lot of analysis Senthil has done to really show that, how communication reduces agent here. So this is just where we are, but we also tested on real lab, except my lab only has a few robots. So this is simple setting in an academic lab. I don't have the setup like the Amazons have or the company developing some of it. But these are just, testing them in a lab with a bunch of goals. But of course, these are a little bit simple scenarios, much simpler than the one I show in simulation. But indeed, you can use them with computer trajectories and do it. I would love to try more, more number of robots, because real robots bring challenges there. And of course, I will also the first one to say, these lab benchmarks we have are one of the most simplest one. The world is not that simple. We still have a long way to go. So where do we go next year? So one of the things we're looking into, we have a big project at UMD with ARL, Army Research Lab, on Artemis, and one of the challenges we're dealing with is outdoor navigation. You're given big terrain with vegetation. I was talking to John and Maggie this morning about all kind of challenges. They have data sets like rugged and Realis 3D, and you don't have a map. So one of the things we're looking at is when you're dealing with uneven terrain, where you don't even have a line of sight, you have vegetation and obstacles, can we do it? So this is something we are trying right now in the simulators, that can we take these methods and work in outdoor challenging situation? Because my simulation, I was the first one to admit, were very simple 2D circles. And even the lab experiment I showed you, 3 or 4 robots and I split this thing. So maybe in a year or two, I will let you come and tell you, where to go with this. So again, this is just to conclude, I'm seeing a lot of promising results. When I started working on MARL 2-3 years ago, I'll tell you, I was not sure it'll work well, because MARL is something we don't understand as well as the classical methods. But with selective communication, we are seeing really good results. We are very promising, But ultimately, we still think a lot of work to be done. Can we take this inside formation theory? I still think we can do much better work, and maybe someday, someday we'll be able to learn how biological organisms do it, and maybe someday do things. So just to conclude, I'll just stop here and acknowledge all my sponsors, especially, as I said, we have a lot of Army collaboration, but also want to acknowledge our collaboration with Amazon, and also with Google. I'm doing some work on doing large language models for this problem. I think I'll just stop here and take time for questions or feedback.
Questions from the audience?
Hello, thank you for I need a clarification on the definition. If you train the communication between agents by allowing them to pass, is it not on?
I don't know, but can folks on Zoom hear it? I guess that's a big challenge.
That'll be a challenge.
Does this work now? Okay.
I'll repeat the question.
So if you train communication between agents by allowing them to pass gradients while training, is it technically still a multi-agent system? Is it not a single-agent, multi-body system? The counterpoint could be that the communication should be through the environment, which is not necessarily differentiable. You also introduced the problem of discretization of messages and so on, but I'm more interested in, is it technically one or the other?
Yeah, so it's a great question. I think if I understand correctly, I'm one of similar people on Zoom. How do you communicate? So one of the things I'll tell you, there are two parts to it. One is, I didn't talk about differentiability. Differentiability is a very important criteria, which I haven't addressed. So yeah, but that's something to have. But as I said, but I'm more interested in what is called implicit or explicit communication. Sometimes the communication environment is something what I call implicit, right? We're just walking, we follow each other. We're not explicitly sending messages to each other. So if I understand your question correctly, the environment part is implicit communication.
Well, I'm also referring to if you use sound. So if you have a
Sure.
simulation where one would emit sound and the other would accept it, but there wouldn't be like a gradient.
Right. I would think of that as implicit communication. Again, to me, implicit is a very broad term, right? I say implicit there. So you're right, we can do implicit or explicit communication. So the thing we trained was selective explicit communication. That's what some of the things we have done. We are seeing very good results with that. Limited amount of selective communication really improve the behavior. Now, but at the same time, if I understand the question correctly, is there are many cases where you don't have that option, right? And if I limit myself to the kind of example you're giving, implicit communication, which is not even differentiable, so is that even multi-agent? I guess that was your first question. And secondly, will it lead to good answers? I don't have, I think we're still in early stage of research. I don't have a precise answer to your question, because ideally speaking, explicit communication is expensive and challenging, but we're seeing a lot of benefits of it. But if I could really get away with good implicit communication, that's the best case scenario.
Thank you.
All right, but still a lot of work to be done.
Thank you. Time for a really quick.
Thank you very much, great talk. So I guess a lot of people in the controls community ask about like guarantees, safety guarantees of these RL methods when you deploy them.
Sure.
I guess, what's your experience with that, and are there any things we can do during training or execution to actually make these transferable at the scale you showed in the simulation to real world?
So that's the biggest question, everybody. I have a lot of people working on formal methods. There's a whole community. We just hired some very good colleague at UMD, Karen Belta. He's control and does great work. So this is the biggest explainability. In fact, I just put together a monograph on reinforcement learning explainability. Now, any reinforcement learning method, including all the papers I presented, is very hard to give guarantees. I'll be very blunt with you. Okay, so that's it. And you're right, in many situations we do. That's one of the reasons with MPC, I showed you, like on Astro, with MPC, I can give you guarantees. I'm showing great result with MARL, but I cannot give you guarantees. So I'm probably showing you the good benchmarks to you. So this is one of the biggest thing. We see all amazing results from all this kind of learning methods. Reinforcement learning and navigation is a huge success, MARL, but giving any kind of explainability or guarantees is still very hard. I think, but we're seeing some good, very amazing empirical performance. but we are struggling to give any theoretical guarantees. And then what do we do? Someday we'll have a better understanding of what kind of reward function policy optimization will do it. Maybe 5 years from now, we'll have a better understanding of that. But that's a great question.
Thank you. Let's thank